Yeah, as Tommy mentioned, I'm Marcel. I'm a platform engineer at GiantSwarm. I've been with GiantSwarm for quite a while now. So my daily tasks are working on Kubernetes operators or working on Kubernetes, currently more focusing also on the DevOps side of things with Flux and GitOps and so on. But I've also done a lot of other work around cluster API, for example, and management of Kubernetes clusters. Additionally to that, I'm also a Kyverno maintainer. So what I'm going to be presenting today, I'm also presenting a little bit from the maintainer point of view. Maintainer means essentially I've been a contributor to Kyverno for quite some time, and now I also review pull requests and have the power to merge them and so on. So most of them are just maintainer related things going on. So let's get started. Policy management with Kyverno. I want to start with a very simple introduction. And the introduction is going to be, well, what is a use case you might have seen if you are around on Kubernetes, and something that has plagued Kubernetes developers and users for ages, and that is requests and limits. So in general, requests and limits should be set on any deployment/pod that is running in Kubernetes. And that is something that's generally understood. When I was on a conference 3 months ago, there was even a talk that kind of presented this as one of the deadly sins of Kubernetes, right? Not setting your requests and limits as a surefire way to eventually get your cluster to explode because something's going to go wrong. So from that, we kind of get the understanding, hey, we should always create a pod with requests and limits, and not creating a pod with requests and limits should just not be allowed. And additionally, from a user point of view, Kubernetes should be responsible for enforcing this. And this is how we kind of get to the topic of, well, what is actually the Kubernetes native solution for this problem? Like before we get to Kyverno, we're going to go through what is actually the Kubernetes approach to get to this solution. Well, now let's take a look at how Kubernetes interprets this. First of all, we need to understand the basics. Every time I do a talk, I kind of want to cover the basics as well. This might be very basic for some people, but I think reiterating it isn't necessarily a problem, because also for you, it reinforces this knowledge and also hopefully reinforces some understanding of how Kubernetes works. So first of all, we need to understand that every request that reaches Kubernetes reaches the control plane first. What does that mean? Every kubectl command you run, like if you do kubectl apply, kubectl get, goes directly to the control plane. I often have even interviews with people that apply to us or like talk to people at conferences, and they are not entirely certain of this concept. They sometimes think requests go directly to nodes or to kubelets or so on, but the main part is the control plane is the central place where all your requests end up. Even requests inside the cluster. So if a pod is running a request for which other pods are running, it will talk to the Kubernetes control plane. This is very fundamental to understand, in my opinion. And from there, it is also quite fundamental to understand, well, which parts are running inside the control plane. And I've kind of shown 4 parts here. The first part is the API. That's where every request goes through. So every request that reaches Kubernetes goes through the Kubernetes API. And from there, it kind of fans out. There's like 3 things it fans out to. One is the scheduler. If you have a request that requires scheduling, scheduler will be involved. etcd will be involved for persisting whatever you're doing. So the entire Kubernetes state is essentially stored in etcd. What that means is if you create a pod, the pod doesn't exist until it's in etcd and is really persisted there. And then the controller manager. The controller manager is responsible for general tasks in Kubernetes that are base Kubernetes functionalities, for example, transforming a deployment into a replica set, and the replica set into pods. All of this logic is in the controller manager. The main takeaway from this is the API, or the Kubernetes API, is the central place where all requests go through. And it's therefore also the central place where we need to deny requests. So if you want to deny a request of like a pod doesn't have requests and limits set, we logically have to do it in the Kubernetes API. And that's exactly what Kubernetes is doing. So now let's look next at how does the Kubernetes API internally work for denying and mutating requests. First of all, we imagine we're sending a request to the Kubernetes API, and we start on the far left here. That is our request. Imagine this to be kubectl apply my deployment, or kubectl apply my pod. First of all, we obviously need to go through authentication authorization. So am I the person I pretend to be, and am I allowed to do what I'm trying to do? Like, for example, am I allowed to create a deployment? So this should be quite logical. And then the next step is already related to admission control, and also what later Kyverno will be doing. And that is mutating admission. What does mutating admission even mean? This means the request is changed. And this is done through a webhook system. So the Kubernetes API will call out to a webhook. The webhook will somehow mutate our request, send it back to the Kubernetes API, and then the next webhook will do the next mutation. What does that mean for our, for example, deployment example, where we have maybe not requests and limits set? This means here we could default requests and limits. We will see this later on in the demo as well. So we could mutate the request to just add some requests and limits. Then the webhook would send this back to the Kubernetes API, and we go through the next webhook, which maybe does something else. Very important to note here is that these mutating webhooks are run in sequence and not in parallel. Why is this important? This kind of means that each time we send something to a webhook, the webhook needs to send it back, we are wasting time on the overall request, right? If there's a lot of chains of mutating requests, we could exceed the context deadline. The context deadline means this is how long Kubernetes will actually wait for your request to be processed. And usually that's like 5 seconds. And if we go over this deadline, Kubernetes API will just give up on your requests and will send back like context deadline exceeded. You might have seen this if you interact with Kubernetes a lot. So far, so good. So we have maybe mutated our requests, but we still haven't found any functionality to deny anything. And this comes a little bit later on. But first, we also do object schema validation. What does that mean? Object schema validation is simply, is whatever we send to the Kubernetes API actually a valid object right now? Imagine a deployment without a type. That is not a valid object. Kubernetes would automatically reject that here without any more webhooks. If you have ever seen a custom resource definition, this is the evaluation of this custom resource definition, which can be done with the open API schema. So this is what happens here, just some basic schema validation. And then finally, we get to the next interesting part for us, and that is validating admission. So on the one hand, we have mutating admission. On the other hand, we have validating admission. Mutating admission, we just talked about, we change stuff. Validating admission, we're now validating that the object is as we expect it to be. And this is exactly where we would now have a webhook that checks, hey, does our pod or our deployment have requests and limits set? Well, we would need to implement a webhook, and then here we could decide, no, at this point, all the changes to the object are done. It doesn't have requests and limits, now reject the object. And then we go to persist the object into etcd, and then the whole normal Kubernetes flow would start. Once again, we see that here are webhooks handling these requests. So the Kubernetes API would send a request to the individual webhooks, which are registered, and the webhooks will respond to the Kubernetes API. Interesting to note here is that these are happening in parallel. So the Kubernetes API will not send the requests in sequence, but will send all of the requests at once. So if there's 15 validating admission webhooks, the Kubernetes API will just send all 15 requests at once and then wait for each of them to respond. If all of them have responded, it will then proceed to the next step. So far, so good, right? We've kind of understood how admission control works in Kubernetes to the extent that we know, okay, there's a point where we mutate stuff and there's a point where we validate stuff. As soon as we want to extend anything, we have to implement a webhook. The webhooks are run in sequence during mutation and are run in parallel during validation. All of this should be kind of logical now. So the next normal question would be, well, how do I even register one of those webhooks, right? So far, we just talked about somehow these webhooks exist and they are there for validation and for mutation. Well, webhooks are also registered declaratively in the Kubernetes API. That means there's two specific types which handle webhook configuration, and that is the validating webhook configuration and the mutating webhook configuration. And this configuration contains a reference to a service which has to implement the actual logic. So imagine if we have a mutating webhook, we need to create a mutating webhook configuration which points to the service which actually implements the mutating webhook logic. So far, so good. So let's look at one of these examples. And I've kind of put this on a slide here. I will just go through some of the most important parts. First of all, we see obviously, hey, it's a validating webhook configuration. And we also see a set of rules. So for example, hey, we want to apply this to the creation of pods, which are namespaced. They're always namespaced, but we still have to offer a scope here. And then we have the client config, which particularly shows the namespace and the name of the service, which is implementing the actual webhook logic. Interestingly, we also see here the timeout for the specific validating webhook, which is set to 5 seconds. And we have side effects should be none, because we're just validating something. There shouldn't be an additional object created just because we validated something. And these have to be created for each registration of a webhook. Now, interesting for you as a user of Kubernetes is sometimes, and this can also happen with Kyverno, we will get to this a little bit later, but whenever you see that lots of requests are getting denied and you can't quite figure out what's going on, like everything in your cluster seems kind of stuck, check which validating webhook configurations and which mutating webhook configurations you have. Because a scenario that can happen is your validating webhook is broken and it's just denying every request in your cluster. Therefore, nothing will be created and even the Kubernetes API won't function anymore properly. Or your validating webhook isn't running as expected. Then you need to check which validating webhook configurations do I have and are the services running as I intend them to run? And if you can't figure out what's going on, sometimes, I'm not saying this is security advice, but sometimes just deleting the validating webhook configuration, which you can always do, can unstuck your cluster. Just as a side tangent on this slide. So, okay, we've gone so far as to see we have these webhooks, we know how to register them, we need a validating webhook configuration or mutating webhook configuration. Well, how do I implement one? So there's first of all the way of do it yourself. As you know, we're in a Kyverno webinar right now. This is not what we're going to go with, but in theory, this is a possibility. So you can implement a webhook in whichever programming language you want. There's good library support for popular languages such as Python and Go. And therefore, you could just write your own microservice, which is a webhook, and then handles whichever validating or mutating configuration you want to do or logic you want to do. I have to caution against this a little bit because we've also done this in the past. Obviously, we also like writing code at Giant Swarm, and before really Kyverno or similar toolings existed, we've also wrote our own microservices to do this. But it's not to be underestimated how much effort this really is, right? Because not only do you need to implement the service, you also need to maintain the service. This means all your dependencies have to be kept up to date. All your logic has to be kept up to date. You have to deal with a lot of different things to simply add a webhook inside Kubernetes that handles the specific logic. So for us, the churn was quite noticeable. Okay, what are the other options, obviously? Well, the other option is to use policy management tools, and this is what we're here to talk about mostly. And there's currently two popular choices, which I still both want to mention, even though we focus on one of them. One is Open Policy Agent Gatekeeper, which uses Rego for policies. Rego is its own language, it's a validating language. You can find a lot of information on it. The main difference is Rego is not only intended for the Kubernetes use case, but it's a general purpose validation language. So it's not only bound to the Kubernetes space. And Open Policy Agent Gatekeeper mostly covers the validation policies. As we saw previously, there's a mutating case and there's a validating case. Open Policy Agent has the mutating case in, I think, an alpha stage currently, alpha or beta stage. Like they did a lot of iteration to handle this with Rego, but the validating policies is really what it focuses on currently. And the second one, the second popular one, in my opinion, is Kyverno, the one I want to focus on here, obviously. And Kyverno is really focused on the Kubernetes ecosystem alone. It doesn't have any applicability outside of Kubernetes. Kyverno always assumes to be running inside of Kubernetes and always focuses to be a Kubernetes native policy management. That also means any logic should kind of be confined to the Kubernetes space. And in here, we have multiple use cases we will go through later on. So for example, we have validation, mutation, and generation use cases. So you cannot only validate and mutate resources, you can also have some generation use cases where you want to generate an additional resource on a specific request. So what are the goals for Kyverno to kind of get a little bit more motivation going on, like why use Kyverno? First of all, Kyverno tries to represent policies as Kubernetes resources. And we will see this in the demo in a few minutes. So what it really strives to do is, hey, we have policies and we try to show them as Kubernetes resources. So it's Kubernetes native to interact with them. So you can kubectl get your different policies and see, hey, this is what's going on. And these are the policies which are registered. Additionally, it strives to have a simple mechanism for validation and mutation. So Kyverno went a little bit the other way. It didn't try to implement its own language or like use an existing validation language, but it tries to represent validation mutation use cases in YAML with like some James path or similar just query languages to kind of get to a state of, hey, we can validate or mutate something. We will also see this in the demo a bit more, but it's a fundamental difference in the approach, because the approach is more to cover 80% of the use cases that are usually hitting customers, but for very complex use cases, Kyverno might not be the right tooling, but it still tries to cover Kubernetes specific use cases. So it's not really applicable outside of Kubernetes. And as soon as you stray outside of what's normal or accepted in Kubernetes, you might run into problems, obviously. So far, so good. Let's look at the architecture of Kyverno before we really get into it. And here we can, on the top, see again, what does it actually look like in terms of where does Kyverno hook in? And those are the two places you would expect. Number one, the mutating admission, and number two, the validating admission. And you can see Kyverno registers itself as a mutating webhook and as a validating webhook. What does that mean? That means that Kyverno does not try and register multiple webhooks or try to replicate that there are multiple actual policies and somehow do multiple webhooks. No, Kyverno centralizes the entire policy management in one service, where one service handles all mutating admission requests and all validating admission requests. And from there, internal Kyverno then has the webhooks which are registered and the monitoring of these webhooks. So this is another benefit to implementing it yourself. With Kyverno, you have monitoring built in and you get metrics on how the webhooks are actually performing out of the box. And then you have two controllers. One is the policy controller, which essentially applies the policies of mutate and validation. And you have a generate controller. A generate controller is especially useful if you want to generate additional objects to your request. Therefore, it's kind of moved out of the policy controller because it's not necessarily the normal use case of mutating and validation. Therefore, it's kind of moved out as like an additional use case. From here, let's actually look at a policy example. So we will go through an example of a policy, and this policy obviously is topical, require requests and limits. Okay, so we want our deployment to have limits set and have some requests set. So we see here, it's just a custom resource definition. In this case, the kind is cluster policy. Cluster policy means it's a non-namespaced resource. It will live non-namespaced and will be, yeah, on a cluster level. And from here, we can just see the metadata name and the spec. And inside the spec, we have a set of rules. The rules are usually executed in order and then can be validation or mutation rules. And here we see a rule that just says validate resources, and we want to match a specific resource kind, which is the pod. So we want to cover each use case where possibly a pod is created and want to say, hey, for every pod that could possibly be created, we want to validate the following terms. And here it's quite easy. We just say we want to validate. The message is the message that should be returned to the user, essentially saying this is what the user should get as feedback if the validation fails. And then we can see, okay, we have a validation pattern, which just says the spec of a pod should have containers. Each container should have a request, which is just anything. So memory question mark star means any value should be in here. CPU question mark stars means any value should be in here. And limits, we want to set a memory limit, or any memory limit should be set. So what this policy essentially does is, hey, we have a cluster policy. It validates that any pod that is created has at least requests for memory and CPU, and it has a limit for memory set. This is what we are enforcing now. Wow, that was a lot of talking and a lot of different stuff going on. The sun is shining on me. I'm starting to slightly sweat in cold Aachen. But let's get actually started and see how this looks like in reality. Like, let's look at a demo. For the demo, I have my terminal set up here. Inside the terminal, I have set up in a kind cluster. Particularly, I have set up Kyverno. So Kyverno, you see in the Kyverno namespace, there's just my Kyverno pod running. Now, here's the disclaimer that is not true for the demo, but should be true for every single one of you ever using Kyverno in a serious use case. Never run Kyverno as a single replica unless you're doing a demo in a webinar. A single replica means if this replica is dead, Kyverno will no longer respond to any request, right? Any validation request will fail. Any mutation request will fail. Nothing will work. Have 3 replicas at least. So HA. In Kyverno, you can just simply set in the Kyverno deployment, hey, I want 3 replicas. Kyverno will do the leader election. Kyverno will do everything and fan out the requests to all 3 replicas. Then you're more on the safe side. Never, ever run a validating or mutating webhook in a single replica unless you're doing a demo. So just for reference. Cool. So we have this set up, and I have prepared some demos. So I have prepared the scenario here. I hope this is all readable. And we can see we have 2 deployments. We have one deployment. No requests and limits are set. Bad deployment. And we have another deployment. We have requests and limits set. Good deployment. Both deployments are super simple. I'm just using BusyBox for demo purposes because it really doesn't matter. And we have our policy. This is the same cluster policy I showed on the slides previously. So we are enforcing this policy. So if it fails, the request won't go through. And we are just checking, are memory requests and limits set? So let's get started. I want to first apply my policy because that is kind of important. So in scenario 0, I want to apply my policy. Bam, my policy has been created. And now I want to see if it actually rejects the bad deployment. So the bad deployment was deployment 1, if I remember correctly. And we see, oh, we got rejected. And we got the error message which we expected, which says, hey, CPU and validation error, CPU and memory resource requests and limits are required. So you can see this down here as well. My beautiful policy rejected my request. Now let's see what happens if I submit the valid one and we, as expected, it just works because the policy is like, yeah, you did the right thing. You did it correctly. Now, let's go back a little bit and think about what has happened and some thinking should happen in your brain right now. First of all, this was on a specific kind, which is the pod. But what I created was a deployment. So if you think about it logically from Kubernetes terms, why did my deployment request get denied even though my policy is only for pods? Shouldn't the deployment be created and then all the pods should fail? That's an interesting point, Marcel, that you brought up there. And that is exactly one of the features that Kyverno is doing. So essentially, because we have the resource kind of pod here, Kyverno will expand the policy. And let's look at this really quickly. So we can get the cluster policies as we can get any other resource. We can take the name of this cluster policy, which is require request and limits. And we can now describe this cluster policy here. And now we see, first of all, we see some events where it like kind of said like yes and no to my beautiful deployments. And now if we scroll up, we suddenly see, hey, Kyverno did something smart. It not only matches to the kind pod, it also generates additional rules for the kinds daemon set, deployment, job, and stateful set. What does this mean? Kyverno will, if you see, hey, I have created a validation policy for a pod, it will also reject a deployment which contains the pod and will translate your specific policy to also match these cases. Why is this smart? You don't want to wait a whole long while for your deployment to be created and then wonder where are all my pods just because they're getting rejected. In reality, what you want is immediate user feedback and say, your deployment is wrong, my friend, it will create the wrong type of pod. So this is one of the features that Kyverno does and that is able to do because it's very Kubernetes centric, right? It's very centric on just Kubernetes will work in a Kyverno context. Really cool feature, in my opinion, really makes usability so much easier because it's just nice. Next scenario. Hold on, let me clean up first. Make tidy. I've written some make files to make this all a little bit more smooth. Next scenario. So we just reject everything right now, right? If you don't have requests and limits, we're like, get out of here. We don't want your deployment. Now, we still don't want any deployment without requests and limits. But how about we just default some requests and limits if they aren't set? So we as a cluster administrator could say, yes, you have supplied us a pod that doesn't have any requests and limits, but we will graciously go ahead and set requests and limits for you, which we think are applicable. Therefore, every pod will have requests and limits, and you can create your deployment without requests and limits. We will just, default it. Again, here we see we now have a mutate policy. And the mutate policy is structured as such that we, for each over each of the containers in our pod in this case, right? So each pod has a container. Containers have set requests and limits. So we iterate over each container in our pod and check, hey, does it have any requests or limits set? And this plus and bracket basically means if there's no memory set here, add this memory. Or if there's no CPU set here, add the CPU value. And to test this, I want to create two deployments. First of all, a deployment, again, bad deployment, doesn't have any requests and limits. And number two, good deployment, has requests and limits. And we want to check if the requests and limits that were set on this pod are maintained. Here we go. What do we need to do? We need to go to our scenario one. And we need to first create the first policy. And we need to create the second policy. So now we can see when we check the cluster policies, we have two policies. The first one is a mutation policies, which should add the requests and limits, and the action is ordered. So if it fails, we don't fail the whole request, we just audit that it fails. And the second one is the require requests and limits one, which basically says, if you don't have requests and limits by now, something is wrong. So these are the two policies we have right now. And now we can go ahead and we can create our first deployment, the deployment without requests and limits. And we see now that it was created successfully. let us check our deployments. We can see here, we have in the default namespace, the deployment deploy created 6 seconds ago. So we can describe this deployment and we see, hey, we have requests and limits set by Kyverno. And we also have here in the annotation set, hey, Kyverno did something. So it wrote an annotation for us that it added to container 0 requests and limits in this specific path. Beautiful. It all worked. We have a deployment that kind of worked. Now for the second test. So we delete our deployment really quickly. So it's gone again. And we now apply deployment 2. It also creates, because it already has requests and limits set, the difference should now be the requests and limits should be different from these ones. So let's verify this, describe our deployment. And we see here, we have 100 M CPU set and 10 MB bytes. I don't know the correct wording for that, of memory. And we see here, wow, this is entirely different from the other one where we defaulted it. So what we've seen now is, first of all, we can default certain things and then validate them. And we can very easily implement this with 2 separate policies. So far, so good. And you might say, wow, this is already great. But now I tell you, well, there's another case where this might be a little bit problematic. Imagine now everyone just uses suddenly your defaulting, but then you need to change it and everything gets kind of out of whack and you still want people to get to set their own defaults and limits. So what can we do? Let's first of all clean up a little bit again. We can go ahead and create 2 policies again. But we do it a little bit differently now. The first policy is the same. We still want to verify that each deployment and pod has requests and limits set. Nice. The second one is now a little bit more complicated. So I want to go through it a little bit more slowly. The general idea is we want to only default the requests and limits if a specific label on the deployment is set. Why are we trying to do this? Imagine the following scenario, and this is something that, in my opinion, in operations use cases happens quite often. You want to opt in as a user to get certain things defaulted. Like, for example, you want to opt in to a specific company standard, and you don't want to just blast the company standard on everything. In this case, we say, if you have set a specific label on your pod, we want to then go ahead and default the requests and limits. And if you haven't set this label, we will reject your request so that you either opt in into the default requests and limits that kind of the cluster administrator decides, or you supply your own requests and limits and kind of argue why you need specific resources. This is kind of, in my opinion, a pretty common use case. So we want to, again, default requests and limits. We have a set of rules. And now we have a precondition. The precondition is defined to be something that happens before we actually mutate. So we want to check if something is the case before we do the mutation. In this case, we now use this kind of double curly braces to check something on the request object. In this case, we want to on the request object to check if the metadata labels default. So a label with a key default equals, so we have an operator which says equals, there's multiple operators like not equals and so on, or not in, besides the point right now, but we want to check if that specific label value equals yes, please. So if the label with key defaults equals yes, please, then we want to set the requests and limits. If it doesn't equal yes, please, we're not going to do anything. And if they're already there, we also don't want to do anything. So we can see here, this is pretty much the same. We for each over each container and then said, hey, let's set this and do it. So we have 2 deployments again. One bad deployment that, is just bad deployment. And we have second bad deployment, but second bad deployment has set the default yes, please label. So what do we expect? We expect deployment 1 to be rejected because it doesn't get defaulted, it doesn't have the yes, please label. And we want deployment 2, or we expect it to be accepted because it has the yes please label, and everything will work out. So here we go. We need to first go to scenario, 2. Am I misremembering? Scenario 2, yes. And we want to apply the policy 1. And we want to apply policy 2. Both policies exist now. Now we want to first create the bad deployment, which should be rejected, if I remember correctly in my brain. And we see it is rejected. Validation error, CPU and memory resource requests are not set. You did bad deployment. And now we go for deployment 2, and it's created because the yes please label was set. So this is a slightly advanced use case for Kyverno, where you can utilize preconditions to really enforce company policy. And this is where I think Kyverno really strikes. It is very Kubernetes centric, and it covers a lot of the use cases, in my opinion, you will find in a corporate environment. I need to check my time a little bit, running a little bit low on time, but I want to do one more example, a really brief one. Which is now going to be in a different context. So far, we only talked about deployments. We only talked about certain use cases with requests and limits. Let's talk about a slightly different use case. And that use case is going to be, we have a namespace. When a namespace is created, I want to create a network policy. This is for the security folks, because sometimes new namespaces are allowed to be created, but in each namespace, you want to have a network policy which denies all traffic, so that people will create their own network policies inside your clusters. Beautiful. So we have a policy now, which is a generate policy, meaning we send a request for one specific type, in this case, namespace, but we generate a completely different object. This is kind of also a built-in feature in Kyverno, which is essentially a side effect, but it's done in a pretty smart way, in my opinion. And therefore, for certain use cases, it's very valuable. Use cases like this. What I do want to caution you is, remember that this is a side effect. You're doing one request and something else happens somewhere else. This is not necessarily apparent to the user. So I would mostly say use this for security reasons or for reasons for company policy, which is extremely strict, because it's not necessarily user-friendly, because you're doing something completely different from the request that the user potentially did. Enough talking about that. What are we doing? If a namespace is created, we exclude a set of namespaces. So if the kube system namespace is created, we don't want to deny all traffic in the kube system namespace or several others. But if another namespace is created, we want to generate a new custom resource, and the custom resource is network policy. In this case, deny all traffic in the namespace where the request is coming from, and just like deny everything. So let's go ahead and do this. First, I need to clean up again, I think. So we'll make tidy. We are now in scenario 3, and we want to create our policy. Bam. We have our policy created. And now what we want to do is first we want to verify there's no network policies at all in this cluster, because the local cluster. So no network policies are running at all. And now what I want to do is I want to create my namespace, and I want to verify that a network policy was created. I do this. I check the network policies. Kyverno created my beautiful network policy in my namespace. So this is just to show another use case of Kyverno. From here, I have one last scenario, but I'm just going to explain it really quickly because I don't think we have the time. If we have additional time at the end, I can show it then. Essentially, what we're doing is create a deployment in a namespace and make sure, this is the policy, this is why I don't want to go through all of it, but what the policy essentially does is it checks if the deployment has a specific network policy assigned to itself. What that means is every deployment being created needs to create its own network policy to kind of say, I want this traffic to be allowed. There's no way anymore to say, I don't want any traffic. You need to specifically state which traffic should be incoming and outgoing and so on. It basically enforces every deployment to have a matching network policy. And this is the policy for that. And you can see here, we're actually doing now an API request to check if any network policies exist already. And this is another feature in Kyverno, where you can check any resource in the cluster and check, does it actually exist? If no, we fail the validation. Beautiful. Let's go back to the slides. Please, computer, I would like to see the slides. Yes. So we've seen a small demo of different use cases for Kyverno. And from here, I just kind of wanted to talk about, what about existing Kyverno policies, right? Like, you don't want to write all these policies by yourself. And thankfully, Kyverno has a very large library right now of existing policies, which you can just take and put into your cluster. Since everything is a custom resource, you can just take the existing policies for your specific use case and say, hey, I want this policy. kubectl applied in your cluster if you're bad. Otherwise, you can just put it in your CI/CD system and apply these policies to each cluster you manage. The main collection areas right now are best practices. So best practices like setting specific labels, setting specific annotations, enforcing certain best practices in Kubernetes. And the other one is security around PSPs especially, and other security relevant areas like I just showed with network policy creation. These are the two areas where really Kyverno has existing policies. We're very open also now, speaking as a maintainer of Kyverno, for new policies to be presented here. And there's Chip Zoller, he's another maintainer of Kyverno. He's very active there and really encourages people to contribute their policies. If you have built something nice, this is the way to put it. Now, going back a little bit to the policy management as a company area, I briefly want to talk about how can you actually collaborate on Kyverno in a multi-team environment. And the main thing to do here is to basically write your own policies. Since all of them are custom resources, each team can deploy its policies independently of any other team. There are a few little nooks though, little things to be careful about. You can write multiple Kyverno policies which are contradictory. Kyverno checks essentially the validity of individual policies. It does not check the validity of all policies together, because as you can imagine, this is an extremely difficult problem to solve. Therefore, you can run into cases where team 1 creates a specific policy, team 2 creates a specific policy in the same area, and the two policies contradict each other. Worst case scenario is you have two validation policies. One says you have to have requests and limits, and the other one would say you are not allowed to have requests and limits. The obvious outcome is every request will be denied because it's it's not possible to verify both statements. So this is something where you still need to collaborate, but the deployment and the management can be completely separated out to different teams. And also running Kyverno itself can be run as a service, and therefore you can just do it as you please. Now, some conclusions from my side, since we are reaching we're already over 45 minutes. Some conclusions. Reading and creating policies is simple in Kyverno, in my opinion. It is much easier than using Rego. From a person that already handles a lot of YAML, I feel like more at home handling more YAML. Additionally, complex policies use JamesPath in Kyverno, which kind of means you need to handle JamesPath sometimes. There's a CLI for JamesPath. It's nice enough to use, but yeah, it's okay, I would say. Validation, mutation, generation policies can be implemented. It's all possible. These use cases are covered. Kyverno strives to go around this 80-20 rule. 80% of the use cases that exist should be covered. The 20% niche use cases should be enabled, but are not necessarily covered in Kyverno. So unless you're doing something very out of the box with Kubernetes, your use cases should be covered by Kyverno. Additionally, metrics and audit reports are built in. Let me actually check something right now, because I had a small problem earlier. I wanted to show the policy reporter UI, but it's loading. It's my little setup locally, but I will show it maybe later on. So essentially, there's a policy reporter UI, which shows you the metrics and reports, and also shows you different breakdowns of which resources are actually failing right now, which policies and so on. All of this is built into Kyverno, and you don't need to re-implement it yourself. You can hook up your Prometheus to it. You can do whatever you please with it. It exists, is what I'm trying to say. And it also exists for auditing and security contexts. Finally, and this is the one point where I can see people striving away from Kyverno, complex policies are hard/impossible to implement. What do I mean with complex policies? Complex policies can be something like you need to do multiple requests for multiple different objects, and you need to have, for example, mutation in a very specific order with lots of API calls to verify something. This is in Kyverno hard to do. It is possible, but it is hard. And then there are some cases where you need to really parse a lot of YAML from config maps or from other objects. This is also where it gets kind of around the edges of this is not entirely covered anymore. So if you really have complex use cases, you sometimes need to spend a bit more time to write your policy. And additionally, it might sometimes be impossible to verify your constraints or to really make it work in Kyverno, just simply because Kyverno tries to simplify writing a policy. And that in turn means very complex use cases cannot be implemented in such a simplified system. But also I can say that as a maintainer working on covering more of these use cases, especially parsing YAML, working with YAML, and for example, reading a YAML file from a config map and then doing something based on what is inside the config file and so on and modifying it. This is something I'm personally passionate about. So this is also something I'm contributing to in Kyverno itself. And this is it on what I had prepared. I saw there were many questions. Therefore, I think we can go through some of them.